So I begin my lecture by asking the question that what is electronic design? What do we really mean by electronic design? So an electronic design means we want to develop a circuit or so by connecting some devices such that our specifications are met, and the specifications are typically in the form of a behavioral description of the circuit. We can specify the functionality of the circuit without specifying intricate details what the circuit is going to be built up of, and we are going to build the circuit. So if we define an electronic design from that perspective, then implicitly it boils down to the fact that electronic design is the process of transforming a behavioral description of the circuit, which indicates its specifications, into a structural interconnection of the components with which the circuit is built up of. So with this we can define any circuit, be it a discrete or integrated. Now when it comes to an integrated circuit, which means we talk of SSI, LSI, MSI, VLSI, ULSI, whatever level of integration be it, it even comes to some more restrictions being put on in terms of developing the circuit. So after getting ensured about what are the components with which we are going to build the circuit, we translate the interconnection of components into some geometric patterns that we transfer onto some silicon wafer during a typical lithographic process and develop the circuit on it. So this physical design again involves various steps which we shall see a couple of minutes later. That involves sizing the devices, then partitioning, floor planning, placement, routing, compaction, and various other steps which we shall see in due course. So if you see a typical digital hardware design flow, so let's talk of digital design only, since we are ultimately looking out to develop a processor. So let's talk of digital design only. Of course, processor doesn't mean only the digital technology. You can have an analog processor also that can accept analog signals, perform computation on it purely in the analog domain, and can present results that are purely analog. So processor doesn't mean it should be digital. Processor can mean an analog processor also. And although in the middle there was a period when the notion of analog signal processing totally wiped out, and that's why it's not there in the curriculum these days, but believe me, research has come to a point at which people have again started rethinking whether we can whatever we are doing, whatever signal processing we are doing in the digital domain, can we really do it in the analog domain or not. And in fact, analog signal processing really leads to a lot of saving of the circuit area, because you are saving the space for digital to analog and analog to digital conversion. Okay, let's for the time being, for this LBD course, let's get concentrated with the digital stuff only. But keep in mind that processor means it can be an analog processor, it can be a digital processor. So like in any engineering design process, we start by clearly defining the requirements of the design process, which means we define what we are going to require from the particular circuit design. That requirements is translated into a behavioral model, which basically visualizes the system as an algorithm or a process without referring at all into its structural details. So the behavioral model can be simulated for its timing and power measurements. Of course, at the behavioral level, we can still get a very crude estimate of the area. However, the area estimate that we get at the end of this behavioral modeling phase is a very crude estimate, and I myself have found out while I was developing some behavioral model of a circuit that when you come up with the final transistor level implementation or even the layout design of it, you can even minimize 40% of the, as much as 40% of the circuit area by going through different optimization phases when you are doing the gate level modeling, transistor level modeling, layout design, and so on. But nevertheless, we can still have a crude estimate of the circuit area in the behavioral modeling phase. Next comes the Rtl modeling phase, in which you visualize the circuit as an interconnection of register transfer level components, and then you should perform the Rtl simulation. So these Rtl components are typically need not be that you are visualizing the circuit as a collection of some registers only. It can have other middle level components like multiplexers, decoders, encoders, and so on. So all these components we collectively call them as register transfer level components, and the circuit is visualized as an interconnection of these register transfer level components. We don't take care of all the signal integrity issues, timing, and other issues when we talk of the Rtl model, although we do the timing simulation, but in the design itself we don't really directly take into consideration all the low level effects over here. Yeah, I am in fact going to talk in details about simulation in the course of my lecture. So this behavioral modeling and Rtl modeling we popularly do using this HDL simulation. I will talk of what we really mean by a HDL later in my lecture. So for now, just keep in mind that there are two popular types of HDL being used. One is the VHDL and the other one is verilog. Apart from that, there are numerous other HDLs available like System C, System Verilog. Now BlueSpec has come up with some version of Verilog that is called BlueSpec System Verilog. So lots of such hardware description languages are available, which target at a different levels of abstraction in the entire hardware design flow process. The Rtl model is then translated into an interconnection of logic gates, which we call the logic level model of the system, and therefore now you can perform accurate power estimation, then timing considerations. So power estimation, how we can make at the gate level, can you give me any idea? Typically I would like to take an interactive class, not just I'll deliver it one way and you will listen it. I also want you to put your own ideas in course of the lectures. Any idea on how we can estimate the power at the logic level? Huh? No, actually at the logic level we can have an option of choosing what type of logic family we are going to use for further coming down to the transistor level. So at the once you can define a circuit as an interconnection of logic gates, you can straightforward say whether you can go for the complementary CMOS logic or pass transistor logic, or pseudo NMOS logic or complementary pass transistor logic, or Preacher-G evaluate logic or domino logic, whatever be it, to implement your circuit as an interconnection of transistors or so. And depending upon the type of interconnection in terms of the transistor level implementation, you can get an estimate of the power dissipation when you are doing the gate level modeling and simulation. And for doing this gate level simulation, of course you need to generate the gate level netlist. Do you have any idea of netlist? A netlist is basically a specification of interconnection of components in a circuit in a formal way. So there are two ways by which we can express the interconnection of components in a circuit. We can specify the individual components of a circuit and specify the pins that are connected to it, or we can take up individual nets or wires and specify the components that are connected to it. In the former case, we call it a component oriented netlist or a module oriented netlist, and the latter case we call it a net oriented netlist. Yeah, typically in all circuits are basically a connection or a combination of components. Even if it is a sequential logic network also, you know where to plug in your clock pulse generator, where to give the feedback and so on. So again, you can specify your circuit as an interconnection of components using a netlist, even if it is a sequential logic circuit also. Now normally in a digital design flow, since the transistor level design of the circuit is very regular, that means for a particular design we know how we can implement the circuit by an interconnection of transistors. Normally in a typical CAD tool flow, we directly go from the logic level to the physical level or layout design process. However, I should also try to tell you in this context, because some of you may be interested with researches also. Now we are at such a level of design that we even try to, after very much well defining a gate level design, we again try to find out whether we can further optimize the circuit at the transistor level or so. And therefore, between the logic level and the floor planning comes another level of transistor level design and implementation of the circuit. Now in the floor planning phase, we define the different areas on the chip where we are going to approximately place the different components, and later on during the placement phase you finalize the location and size of the different components of the circuit. After the placement phase, you are certain with the different the sizes of the different components of the circuit and where the different components are placed in the chip. So now you have to interconnect the various components. That's what you do in the routing phase. Now in all these phases, you have to go through elaborate testing and verification. Okay. Now after the layout is finalized, then one of the important tasks that you should do is a schematic versus layout verification. What schematic you have finalized, and that gives you a certain set of results. You should see whether after generating the layout you are getting the same set of results approximately or not. Of course you won't get the same set of exactly the same set of results as you were getting in the schematic simulation, because when you were doing the schematic simulation you were not taking into account the effects of the parasitic resistances and capacitances of the interconnects, and those things are taken into consideration when you are doing the post layout simulation. But that should be within a certain range, and if it is not within that deviation is not within a certain range, then you may have to redo your layout so as to bring the departure of the post layout simulation from the schematic simulation within the tolerable limits. Now after the chip is fabricated, another important thing is this post silicon validation. you have ensured that the entire circuit is working, simulation results are perfectly okay, you have generated your GDS2 file, which we normally send to an industry for fabricating the chip. After the chip has been turned out by the industry, you go to some testing lab, you test the chip, and you are surprised to see that the results that you are getting after the chip is fabricated is absolutely different from what you were getting when you were doing the simulation. And that is very, very common. Why? Because during the fabrication, lots of things can happen. For example, there can be a certain component can be shorted to the VDD, or certain component can be shorted to the ground. There can be certain circuit breakages of interconnects at certain points or the other. So they can lead to lots of anomalies in the circuit behavior. So once you test it after manufacturing, all these defects are typically excavated. So this is again a very important aspect, that is to carve out an testing algorithm that is exhaustive enough to test the circuit, test all its critical paths and subcritical paths and so on, and at the same time the testing set is small enough so that with that small set of test cases you can test exhaustively the entire behavior of your circuit. So the test engineers have typically taken up this problem to minimize the total number of test cases. So suppose you consider a circuit with some 40 inputs. If the circuit works on binary logic, then if you want to exhaustively test the circuit with all possible test cases, then there will be 2 to the power 40 cases of inputs. That is simply not possible. We have to test a chip with so many inputs with so few time, and therefore we have to try out some intelligent approaches by writing some algorithms by which we minimize the total number of test cases. So now we understand that we are going to implement certain circuits on chip, and those circuits in today's scenario consist of millions upon millions of transistors. So we now understand that these circuits are extremely complex, and there's a popular joke that the complexity of circuits is increasing so much that in few years it will be comparable to living systems. However, looking into the thing from the other way around, although the human beings are developing these circuits, human brain has remained the same over the years. So we have to take into consideration the limitations of human being. So we have to take help of some technology by which we can fasten this design and analysis process. I shouldn't say design, I should say analysis. Normally these tools, they say that with the help of these tools you can design the circuit, but tools are not the designers, human beings are the designers, tools are tools only. So the design has to come from the human intelligence only. So what to do? We have to design a circuit consisting of millions upon millions of transistors, and we are bounded with the human limitations. So let's take the help of some technology which is already known to us. That is what these software engineers do. So let's try to get something from their typical practices. What are their practices? They go for a top-down approach in which they go for a hierarchical design process, in which they go on modularizing a system into components and subcomponents, ultimately arriving at the elementary level components. So hierarchical design obviously pertains to a modular architecture of the system. And the third thing is, although by circuit we mean a pictorial representation of the schematic, but one of the problems that we faced when we tried to design a tool to analyze the circuit at the early stages is that the machines with the help of which we would model the circuit, they can understand only characters, not the pictures. So we have to find out means by which we can transform our graphical ideas into text-based ideas. And that was basically something taken up by Nagel and his co-workers at UC Berkeley way back in late 60s and early 70s, when Nagel was working for his doctoral thesis at Berkeley. And that's how actually evolved the notion of SPICE. So in SPICE, nowadays by SPICE you mean some GUI based tool where you draw the circuit on some schematic editor and see some waveforms on some nice screens. But I think there are some senior people sitting over here. They will also share their thoughts with me. In fact, when I was a BTech student, at that time we used a DOS based SPICE, where we used an editor just like the same you use for your writing your C programs. We used a DOS editor to write some SPICE code, and then we used to run them using the SPICE compiler and get some waveforms drawn. And those waveforms are not the